Thank you very much, Chris. So, as Chris said, my name is Russell Keith-Magee. If you've heard my name previously, it's probably because of my work on the Django project. I'm a 12-year veteran of the Django core team. I was president of the Django Software Foundation from 2011 to 2015. So, as you can imagine, I have a slightly vested interest in Python and Django and their continued success as a platform. But while the web is still important, both generally and to myself personally, for the last couple of years, I've been looking at a different part of the Python ecosystem. Over the 12 years that I've been involved with Django, the computing world has changed quite significantly. Most notably, we've seen the emergence of a whole new class of computing devices where you can't really run Python. The Beware project is the umbrella under which I've been doing all this work. Beware is a collection of tools and libraries for expanding the reach of Python for developing software, both developer tools and libraries to enable Python development on new platforms like mobile devices and iPads. What I'm going to talk about today is an overview of where Django has come from as a platform, where we are and where we're going. Does Django and Python have any future at all in this sort of new world of mobile technology? Now, in this talk, I'm going to be talking some very high-level concepts and looking at a couple of ways those high-level concepts can be addressed using Django and Python. In some cases, I'm going to be talking about tools and techniques that I'm actually using in production. Other cases, there's just experimental and speculative. But although the examples that I'm going to be presenting today are driven by my experience and my background in the Django community and the Python community, the solutions that I'm going to present are solutions from the Python space. There's nothing inherently Python specific about the problems and the ideas or the approaches that I'm going to be discussing. It's only the specific solutions that are Python specific. So, start things off. Cast your mind back to the halcyon days of 2005 when Django was first released. What did the web look like back then? Well, most websites were fairly simple affairs. You put a URL into the address bar of your browser, you hit load, you got a page back, you clicked on a link, and you got a page back. The technical requirements to deliver that were, by today's standards, pretty simple, and those requirements are reflected in the major design decisions of Django and other web frameworks of that era. You have a models.py file defining a data model. You have a views.py file defining a function for each page on your site that you want to return content. You have a forms.py for defining input handling and data validation. You have a urls.py for defining your URL structure and how the URLs that come in are going to be routed to the various views in your site. You have templates for each view to control how each page looks. The most exotic thing you're likely to have in your tech stack in 2005 is something like memcache. And even that's optional, it's really just there as a performance kick. Now, that's not to say that's all the web was in 2005. Websites like Google Maps existed and they showed you could do all sorts of really sophisticated things with the basic tools that a browser provided at that time. But Google Maps was the exception, not the rule. If you were building a website for a client, most clients weren't going to expect you to deliver Google Maps. They were going to expect flat pages and forms. So let's wind the clock forward to the present day. Over the last 13 years, things have changed quite a bit. We've now got other, more exotic data stores. User expectations of the web interface has changed. Users now want a rich client experience. That means we now have some non-trivial amount of logic happening on the client side, some of which will potentially be duplicating logic that exists on the server. There is pressure to expose an API that third parties can then use for integration, which introduces even more potential for duplication of logic. And this is all assuming that you're still just using the classic web to deliver your content. Increasingly, users are demanding native apps to consume their online content, which puts even more pressure on websites to have good APIs, because that's how the native app is going to interact with your service, and potentially even more duplication of validation logic. Users also want live updates, so we need to introduce real-time channels running in parallel to the main web server. So our beautiful Django architecture from 2005 is now starting to burst at the seams with all sorts of potential for duplication and complexity. This changing set of requirements is one of the reasons why we've seen such a growth in JavaScript and JavaScript frameworks over the last 10 years. Initially, JavaScript was just used for simple DOM manipulation. Then things like jQuery came around to make that DOM manipulation easier. Nowadays, we've got React and Angular and Ember, dozens of others. And each of these frameworks is a response to the increased complexity that users are demanding on the client-side user interface. But unless you're going to throw away the server-side code and replace it with Node.js, Adding a client-side JavaScript framework to the mix doesn't fix any of the underlying architectural problems that our website has. If anything, it makes them worse because now you've got complex client-side code base and a complex server-side code base that both need to be maintained. It might make the client-side code base easier to manage, but it's still a duplicated code base in at least some aspects. And that's the driving force behind the approach that's partially known in some circles as isomorphic JavaScript development. Isomorphic JavaScript is the idea that to avoid the duplication of logic client-side, you use the same code on both the client and the server. And because the client-side only has one implementation option, JavaScript, that means the push has been to take the client logic and migrate it back to the server. Now, of course, this is simple if you're using JavaScript on the server, but it doesn't help you if your server is Django and Python. Now, there are integration libraries that will provide various levels of support here. React, Ember, Angular, they all have their Django plugins or Python support libraries that will help you. But these libraries tend to do one of two things. They either duplicate the rendering logic of React or Ember or whatever on the server side. So you end up with a server-side implementation of parts of React and Ember in a second language, or they run React or Ember or Angular in a separate local web service. The Python implementation then goes off and calls this local JavaScript web service, gets a response, and then passes that response on to the client, which, yeah, works, but it's not exactly elegant or efficient. If you want to extend your isomorphism to include validation rules or model logic, then it gets even harder. I don't know that I've seen any particularly good answers there. But let's back this up a bit. Why is isomorphic JavaScript development being proposed at all? Is it about JavaScript or is it about isomorphism? Are these approaches being proposed because of some inherent superiority of JavaScript as a language? Well, some people certainly think so, and they're totally entitled to that opinion. I personally would challenge the claim. To my mind, the only significant advantage that JavaScript offers is that it is available natively in the browser. And if that's not the very definition if all you have is a hammer, everything looks like a nail, then I don't know what is. Being native in the browser is a huge advantage for web apps. But remember, we're not just looking at the web anymore. We're also looking at mobile as well. And you can't use JavaScript on mobile to write mobile apps natively, at least not without additional tooling. So we're already having a discussion about what language are we going to use. There's also expertise and knowledge outside the JavaScript community that can't be easily migrated. The Python community, for example, has huge stores of scientific and numerical analysis libraries. And that's before you get to any personal taste issues about the strengths or flaws of JavaScript as a language. Don't get me wrong, there are very talented people in the JavaScript world, and there are great resources in the JavaScript community generally. But the computing world has never survived and sustained a language monoculture. Any grand future of future development that is based on a language monoculture is, to my mind, doomed to failure. But if we're going to make our lives easier as developers, we need to have our own internal consistency across platforms. So can we do isomorphic development, but without the JavaScript part? Can we take a Python everywhere approach, or any other language for that matter, and find some way to bridge the one place where your language of choice isn't available, in the browser? Well, okay, let's analyse our actual requirements here. Ignoring the implementation concerns for a moment, what does our modern web development environment look like? Well, once we've got that sorted, maybe we can look at what we need to do to get there and evaluate whether JavaScript really is the best approach. We have a server. On that server is the canonical version of the data that we're storing. And we need to expose a way to manipulate that data. And we need to be able to deliver that data to the client. The client has to be able to request a page of content or a block of content in some way, receive an initially rendered version of that content if it can't hold the rendering instructions natively, and then respond to user inputs, potentially modifying server state. Now that means we need to have something in between the browser and the server coordinating that interaction. Those modifications will be validated server-side too, but the same validation needs to happen on the client side. And then we have mobile platforms. These platforms will also be requesting content, but they already have the rendering instructions in the form of a native app. But the mobile app, a mobile device, will want to modify the server as well, so it needs a way in. Now, for those of you who are old enough, you will have seen this dance a couple of times before. For me, this is at least the second time. Last time around, it was the early 90s, and we were going to achieve isomorphism using Java, which was a response to the bad old days when you had a VT100 DUB terminal or X-Windows terminals connected to a mainframe. As an interesting historical footnote, the very first Django project that I worked on commercially was effectively a replacement for a Java-based rich client. The customer was willing to give up the traditional user interface that they were expecting in favour of the development speed that a Django web app was able to give them. The good news is, because we've been here before, we can learn from the design patterns that worked really well the last time as well. And what pattern worked really well? Well, we've got a data model that persists data. It used to be some custom in-memory thing. Now it's a relational database. We've got a presentation layer where the user can view the data. It used to be a graphical toolkit. Now the browser is our graphical toolkit, or on the mobile device, it's just a different graphical toolkit. And we've got a layer in between controlling the interaction of the two, the business logic coordinating between the model and the view. That's right, after years of thinking of the web in terms of documents and pages, we're right back where we were 30 years ago with model view controller. So, how does this change our view of Django as a web project? Well, the thing we need to do is make sure we have a clean separation between each layer. The easiest way to ensure this is to adopt API-first development and use that API as the controller. Previously, we would have used views with forms to manipulate server state. Now we can be effectively jettisoning the entire forms framework and doing everything through an API. You want to submit data in a form? Sure, by all means, go ahead and use an input type equals text in your HTML to do that. But it should be submitted through an API endpoint, not by posting a multi-part form HTML content to a traditional if request.method equals post view. Now this has a couple of consequences. Firstly, it means our project becomes a lot easier to test. Our testing surface is now the API, not multiple possible views, each of which has its own independent interface into the user model. Secondly, it means you elevate integration to a first-class use case. If you want to make sure you have a public API that is rich and has feature parity with everything that your web user interface can do, force the web user interface to do everything through the API. Lastly, it means the user interface layer becomes simpler. Views are now literally just the process of describing what URLs your site will have and how to render content onto those pages. But it's not quite just as simple as dropping a REST API framework into your project. Your server connection can be unreliable. If you're going to contact the server to do validation, then your user experience is going to be awful. And if you won't be able to use your app at all if you're offline, which happens all the time if you're in Australia, for example. So how do you deal with this problem? Well, at the very least, you're going to need to replicate part of the controller on the client side. And this probably means the validation logic and possibly a version of the models as well. This then raises one fundamental problem we can't avoid. We need to have the ability to replicate some or all of the controller logic on the client side. And if we're planning to use Python on the server side, then we're going to need to have a way to get Python running on the client. So what options do we have? Well, we actually have a couple, and we have a couple more on the horizon. Python and Sculpt are two full implementations of Python written in JavaScript. PyPy.js is also an implementation of Python in the browser, but it gets there through a slightly different route. It uses Nscripton, which is a Clang compiler backend that outputs, instead of outputting system native binaries, it outputs a restricted subset of JavaScript called ASM.js. PyPy.js is the C source code of PyPy, the JIT-optimized Python implementation, compiled to ASM.js. Python and Sculpt both shake out to about 500 kilobytes of JavaScript code once they've been minified. PyPy.js is about 15 megabyte, but they all let you use Python in the browser, and they access the DOM as if it was a native set of APIs. So you can have your snippet of HTML on a page with an input and a button, and then a script tag describing how to respond. But instead of the script being in JavaScript, it's written in Python. And you can read the DOM, manipulate DOM elements, install handlers, just as you would with any other platform. And just to be clear here, this isn't like CoffeeScript. This isn't a Python-like language that is interpreted into JavaScript at runtime. It is Python that is running. Does it work? Yeah. You go to the Python and Sculpt pages right now, you can see examples of sites written entirely in Python. In the case of Sculpt, they even give you an interactive prompt to play around with. Now, there are two significant problems with this approach. The first you'll notice is if you jump onto Python's website right now, before any of the Python on the page will execute at all, the entire 500 kilobyte payload of the runtime needs to download first. On mobile, that's definitely noticeable. In a room like this, with a bunch of geeks all hitting the server at the same time, you can guess how well that goes. It's even worse for PyPy.js, where it's a 15, 20 megabyte download. There's also some inefficiency here. What you end up with is a full Python interpreter. This includes a full Python parser and compiler, which is something you're going to have to do if you're shipping Python code to the web browser. Now, the upside for PyPy.js is that because it's a JIT compiler, it actually ends up running faster in the browser than CPython does on the same machine, asterisk for suitably selected benchmarks. But the fact that I can say that even tongue-in-cheek is pretty remarkable. Now, again, we need to go back to our requirements here and analyze what we actually need. Do we actually need a full Python interpreter in the browser? Do we actually need to be able to parse, compile, and run Python code? No, we just need to be able to run it. So why not just ship the runnable version of the code? When you execute Python myscript.py, the Python compiler does a couple of things. Firstly, it parses the code into an abstract syntax tree, or an AST. Then that parsed AST is compiled into an intermediate representation. It's called the bytecode representation. Python bytecode is a little bit like assembler. It's a limited number of basic instructions, about 100 all up. And at runtime, the Python interpreter doesn't use the source code at all. It runs the bytecode because it's faster to parse and a smaller target to implement. So if all we need to do is run bytecode, can we take that capability to the browser? Well, yes, and that's what Batavia is. Batavia is a JavaScript implementation of the CPython virtual machine. And because it doesn't need to carry around the full weight of a compiler and a parser, it weighs in at a little over 10 kilobyte once it's been compressed and zipped. That might not sound like much, but then it also doesn't need to do much either. It only needs to implement the 100 basic Python opcodes, a good chunk of which are basic mathematical operations or basic attribute access descriptions. And once you've got those, you can run any Python code you want. How does it work? Well, okay, to see this working, we need to scrape back the surface of how Python works at runtime. Let's say you've got some code you want to run in the browser, say a validation layer for an API endpoint. On the server side, you have a native CPython interpreter. You can define, import any Python method you want to use. And from that method, you can get what's called the code object. That code object contains the compiled definition of the method itself, the arguments it expects, the free variables it has, and so on. And it also contains the bytecode for that method. So if you take that payload, encoded in base 64, you get a string you can send to the browser. And then on the client side, in the browser, as long as you've got that 10 kilobyte Batavia script to start with, you can decode the base 64 back into a byte string, run it through the bytecode interpreter, and you've got running Python in the browser. And, as with Python and Sculpt, you can even access and manipulate the DOM, so you can manipulate the visual appearance of the page as much as you want. Okay, so what's the downside? Well, it's not fast. It's a couple of orders of magnitude slower than CPython on the same machine. But does that matter? Now, remember, what do we need to get out of Python here? We're not mining bitcoins. We just need Python to implement validation logic and some UI control logic. It certainly can't be slow. We want a responsive user interface, but it doesn't need to be lightning fast either, just fast enough. And more importantly, the part that is slow and complex is on the client side, not the server side. So as long as it's fast enough for one user, it will scale as wide as you need. It's also an area where performance is on the cusp of being dramatically improved. I mentioned PyPy.js previously. It uses a subset of JavaScript called ASM.js. ASM.js is really just a first salvo in a much bigger battle. The next piece of the puzzle is WASM, WebAssembly. WASM is, under the hood, the same just JavaScript that ASM.js is, but it's a pre-parsed, ready-to-use in-memory binary representation of JavaScript. The features it exposes are very much like the old-school assembly language programming. It pushes values onto stacks, invoking primitive operations, popping the values off as results. And because it's assembly, we can use the last 70 years of research into building optimized compilers to generate some very interesting results. For example, Dan Callahan from Mozilla recently did a demo where he was taking live video from his webcam and doing edge detection filtering on the image at 60 frames a second in his browser. Unity, the games engine, has been compiled to WASM, so you can run full OpenGL games in the browser. And, okay, sure, there is a performance hit. You know, your twitching gamers aren't going to be particularly satisfied with this, but you're running an OpenGL first-person shooter in the browser. What more do you want? And Rust recently announced the addition of a compiler flag that will take any Rust code that you have and output a WASM module as output. So we're getting to the point where almost any language can be compiled and executed in the browser and produce that output in a format that is performance comparable with a C implementation compiled to run natively. Now, there are some limitations. WASM is only available in the most recent browsers, so it isn't available everywhere. It doesn't have garbage collection, which makes it difficult to use on dynamic languages like Python. And while OpenGL bindings exist, DOM bindings don't, so you can't manipulate the view of your web page. But all of those features are yet. They're all active areas of development in the WASM project at the moment. Okay, so we've redesigned our entire web app to be MVC. We've got a good API on the server side. We're shipping parts of that API to the rich web client to be used for validation and display. Now, okay, we're doing this refactoring primarily originally to make our web interface easier to develop. Along the way, we've actually made web development easier as well. Because once you've got this separation, the rich web client operates exactly the same way as your mobile native app. The only difference is that you use the DOM to draw widgets on the screen instead of a native API layer. So as long as we can write our mobile applications in Python, we're actually pretty close to having a genuine single-source cross-platform architecture. Can it be done? Well, yeah, and that's essentially what the Beware suite is all about. It gives you the tools to do just that. The URL here is a talk I gave at PyCon Australia last year, in which, starting from scratch, I developed a Fahrenheit to Celsius converter, deployed it as a Django single-page web app, a native iOS application, a native Android application, a macOS app, a Windows app, and a GTK app, all with installers ready to go on the simulators or relevant devices in 17 minutes. It's a single Python code base, about 40 lines of code, plus a small collection of command line tools to have the app packaged ready for distribution on those platforms. Let's be clear though, all of this is possible right now, even without Beware's help. Any number of people in this room are already building responsive websites with APIs and live streams and supporting mobile applications and all the fruit. I'm not saying it isn't possible. I'm saying there's a better way. In 2005, it was possible to build websites. But Django and other web frameworks from that era showed that there was a better way to do it, a way to build better web apps with less code. Beware is about doing the same thing for the apps that we do today. Building a wiki or a web poll in 15 minutes is no longer the challenge. For me, success is when a tech bootcamp isn't just building a blog as their one-day web activity. They're building a live chat website with a cross-platform mobile app to go with it. And that might seem optimistic, but I don't think we're actually that far away from it being possible. Details on all these projects and more can be found at pyb.org. Beware is an open source project. We're actively looking for contributors, all levels of experience. We have challenge coins for anybody who does contribute, and stickers if you're into that sort of thing as well. Come see me afterwards, or I'm here for the rest of the week, so happy to chat. We're also actively looking for sponsors to help the rest of support this work. Beware at the present is entirely a volunteer effort. That obviously constrains our rate of development. Financial support means faster progress. Best of all, we can get great tools without having to give up our open source ideals. With that, I'm done. Thank you very much.